So in this lesson, we are going to talk about solving and graphing proportions. And the learning target that goes along with this lesson is that I can use what I know about equivalent ratios and ordered pairs in order to do this. So really everything in this lesson is pieces of things that you have learned before and just kind of putting them together. So the first thing that we want to review is equivalent ratios and what that means. So remember, proportions are just ratios that are equivalent, and equivalent means equal. So as an example, if you have this ratio of 1 liter of salt water for every 250 grams of salt, we can say that is equal to 3 liters of salt water and 750 grams of salt. How do we know this? Well, what did we do to get from 1 liter to 3 liters of salt water? We would have tripled our ratio, or in other words, multiplied by 3. So what does that mean we have to do to the 250 grams of salt? We would have to do the same thing, multiply by 3, because whatever you do to one part of your ratio, you need to match and do to the other part. If I triple the amount of water, I need to triple the amount of salt. So these are equivalent ratios. When they are equivalent, we can also say they are proportional to one another. So we can use what we know about one ratio to find a part of another ratio. Try these on your own, pause the video, and then unpause to see if you get the same answers as me. So if we have the ratio of 5 to 7, which looks very similar to the fraction 5/7, and it's also the same process as finding equivalent fractions, is finding equivalent ratios or proportional ratios. So how did we get from 7 to 21? Well, we multiplied by 3. 7 times 3 is 21. So what does that mean we have to do to 5? Well, we would have to multiply by 3. 5 times 3 is 15. So 5 sevenths is equal to, 5 to 7 is equal to 15 to 21. Over here, we have that 9 to some number y is equal to 3 to 17. So in this case, we have the variable over here on this side, on the bottom part of our ratio, which is fine. We just go in reverse. So what did we do to go from 3 to 9? Well, again, we multiplied by 3. So what do we have to do here to 17? Well, we also have to multiply by 3. 17 times 3 will give you 51. So 9 to 51 is equivalent or proportional to 3 to 17. Now let's take a look at a ratio table. You've seen these in 6th grade, and we just continue using them in 7th grade. So it says that Isaiah sold candy bars to help raise money for his scouting troop. So you can see that your X value, which comes first, is going to be the amount of candy bars sold. And your Y value is going to be the amount of money that he receives every time he sells the candy bars. The question is the amount of candy bars sold proportional to the amount of money he receives? And how do you know? Well, remember, proportional is the same thing as talking about equivalent or equivalency and equal ratios. And there's a few ways that we can look at this. Remember, if you multiply or divide one part of your ratio, you have to multiply or divide the other part by the same amount. So if I want to move from 2 candy bars to 4 candy bars, I would have to multiply by 2, or double the amount of candy bars. But if I double the amount of candy bars, my money should also double as well. So you would multiply 3 times 2. When I multiply 3 times 2, I should get 6. And here I get 5. So no, the candy bars and the money received are not proportional to each other. To double check yourself, you can go a step further and try another one. What if I tried to say 2 candy bars to 12 candy bars? Well, to get from 2 to 12, I would have multiplied by 6. So over here at 3, I should have to do the same thing. 3 times 6 should give me 18, but it doesn't. It's 12. So again, they are not proportional. Another thing you could do is go back to that constant of proportionality, which we talked about a couple of weeks ago. And the constant of proportionality is just taking your X value and dividing it by your Y value. So if we take 2 and divide it by 3, we get 0.6 repeated. If we take 4 divided by 5, we get 0.8. And already you can tell they're not proportional because if their constant of proportionality is different, they're not proportional. So that's another way that you can tell. So now let's talk about taking these proportions and these ratios and putting them on a graph. So the first thing I want to do is we do know that if he sells 2 candy bars, he's going to earn $3. So we're going to fill in the rest of this ratio table using the ratio that we have. And it's very simple. There's an infinite amount of numbers or combinations that you can put in here. But let's just go ahead and pick some lower numbers so we know we can fit it here on the graph. So I'm going to go ahead and take these 2 candy bars and I'm going to multiply it by 2 to get 4 candy bars. Well, if I multiply the number of candy bars by 2, what do I have to multiply the amount of money by? 2. So 3 times 2 is 6. Then I can take the 4, I can take the 2, whatever you want to use, and I can create another number. So I'm going to go ahead and use 6 here. Well, how did I get 6? I went back to 2, and I said 2 times 3 equals 6. So I have to go back here and say 3 times what? Well, 3 times 3. 3 times 3 is 9. And the last one I'll go ahead and do 8. And how did I get 8? There's a couple ways, but let's just go ahead and go from 4. So 4 times 2 would give me 8. So what do I have to do to 6? Do 6 times 2, which would give me 12. So for every 2 candy bars, $3. Every 4 candy bars, $6. 6 candy bars, $9, and so on. But what we can do with these tables is we can put them into a graph or a visual representation. And sometimes it's just easier to see trends when you see them in graph form. So the graphs are going back to that idea of ordered pairs that you learned about in 6th grade, when you have an X value and you have a Y value. So we always go left or right first on the X axis, then we go up and down on the Y. And in class, what I said was, think about it like an elevator. You have to walk onto the elevator before you go up and down the elevator. So you're always going to move across your X-axis before you go up and down your Y. So let's go ahead and graph this. Our first point would be 2, 3. So I'm going to go over 2, up 3, and put a point. My next point would be at 4, 6. So I'm going to go over 4 and up 6. And there's my next point. My next point would be at 6, 9. So I go over 6 and up to 9. And my last point is 8, 12. So I go over 8 and I'm going to go up to 12. So as you can see, there is a trend happening here with the amount of money that Isaiah earns. Bear with me on my line. It's not going to be super straight with this, but do the best I can. You can see that these dots connect to make a straight line. We know that our X values, because it tells us over here, these were the candy bars. And our Y value from over here is our money received. So this was the money. And the more candy bars he sells, the more money he makes. Now you can also look at a graph and tell if it's proportional or not based on one specific thing that really helps. Well, not just one. We need to have this straight line or this relationship. But if that line goes through the origin, and the origin is that dot that sits right there at 0, 0, then you know that yes, this is a proportional relationship. So just to be very clear on this next slide. For the ratios to be proportional, they have to pass through the origin on the graph. So down here, I gave you some examples that just make sense. So if you make an hourly wage, if you're working and you make money per hour, but you work 0 hours, you're going to make $0. If my car's sitting in my driveway and I'm not driving it, I've gone 0 miles. And if I've gone 0 miles, then I've used 0 gallons of gas. So it makes sense that if something's proportional, it should have the coordinate pair 0, 0. If your X is 0, your Y should be 0. And just like in that last graph we did, the line went through the origin, and so it is proportional. So let's go ahead and do another example. Again, it's helpful if you pause the video, try these on your own, and then play the video and see how your answers match with mine. So here they're giving you a graph, and let's just kind of take a look at what the graph's saying. It's talking about money that was donated versus the donations that were matched by benefactors. So we have the money donated down here on our x-axis. So that is going to be our money donated. And then here on our y, we have matched by benefactors. So we're going to say money matched. Now I'm going to go ahead and put some of these values from the graph into the table. So down here at the bottom, you see 0, 0 is an option. So we can go ahead and put 0, 0 if we want. If I go over 100 and I go up 100, there's my next point. So I went over 100, up 100. The next point would be over 200, up 200, 200, 200, and so on. You start to kind of see the pattern. So the question is the relationship of the donations and the matched by benefactors proportional? Well, the answer is yes, and there's a few ways that we can say this. Not only is this a straight line, and they're related to one another, basically meaning that the money donated is increasing as the matched benefactor money is increasing, but it also goes through the origin, and that's the key factor here to make sure to say it is proportional. So yes, it is proportional. The other thing you can do if you're unsure on the graph is say, okay, well, 100 times what would give me 200? Well, 2. Can I do the same thing over here? If I multiply by 2, will I get 200? Yes. We can go back to our good old-fashioned constant of proportionality. 100 divided by 100 is 1. 200 divided by 200 is 1. 300 divided by 300 is 1. So they have the same constant of proportionality. So again, yes, this is a proportional relationship between money donated and the donations matched by benefactor. In this example, we're going to do the same thing. You're given a graph that has on your x-axis age, number of years, and y is your admission price. So if I go over 0, I can go up 6, 0, 6. If I go over 1, I go up 6, 1, 6. Then we have 2, 6, 3, 6, and you start to see the pattern here. Now the question is this a proportional relationship? The answer is no. A couple ways we can tell. Even though this is a nice straight line, it's not a proportional relationship because it does not go through the origin. Also, if you come over here, to get from 1 to 2, you multiply by 2. If I multiply here, I don't get 12, I'm still at 6. Same thing here. Well, actually, that wouldn't even be a whole number, so we don't even have to worry about that. But we could do constant of proportionality. 1 divided by 6 is 1/6. 2 divided by 6 is 1/3. 3 divided by 6 is 1/2. So all of their constants of proportionality are different, which again means no, they are not proportional. Now this one, the point that I want to make here is more so about how the line kind of curves. If you take a look, and again, kind of bear with me on how straight the line is, and some people might say, oh, well, it goes through the origin, so it's a proportional relationship. But the thing is, just because it goes through the origin, if it's not a straight line, if they're not directly related, then no, it's not proportional. But if you're unsure, let's go ahead and plug some values in for x and y to check. So if we go over 1, we go up 0. If we go over 2, we go up 0. If we go over 3, we go up 5. So 3, 5. And if we go over 4, we go up 10. So then you have 4, 10. And you can tell pretty quickly, let's try to just go from 2 to 4. If I go from 2 to 4, I can multiply by 2. But 0 times 2 is not going to give me 10. So no, they're not proportional. It does not work. So even though you have a point of 0, 0, it's not a straight line where they all have this proportional relationship or equivalent constant of proportionality to one another. So no, this is not a proportional relationship graph. And last but not least, let's just do an example of where we take numbers that we have in a table and we put them on a graph to see if they're proportional. So if x is 1 and y is 4, I would go over 1 and up 4. Put my dot. Again, you're always going left and right before going up and down. 2, 5, over 2, up 5. 3, 6, over 3, up 6. And 4, 7, 4, and 7. So this one's kind of tricky because sometimes it can look like it's going to eventually go through an origin, or you're not quite sure because it's a kind of a flat line. So again, even though you draw this, you can kind of, I guess with this one, it's more clear to see that it does not go through the origin. But just to double check yourself, come back over here to your ratios and see if you have any equivalent ratios. So if I go from 1 to 3, I would have to multiply by 3, which means 4 times 3 should give me 12, and it does not. It equals 6. And here I could do 2 times 2 to get 4, but that means 5 times 2 should give me 10, and it does not. It gives me 7. So no, this is not a proportional relationship.